Welcome! In this session, we will dive into problem number 1364, titled Number of Trusted Contacts. Together, we'll explore the problem details, analyze the potential approaches, and review key concepts to solve it effectively. Let's get started. To tackle the problem of identifying trusted contacts, let's first consider the brute force approach. The intuition behind this method is straightforward. For every pair of contacts, we check whether the given trust conditions are satisfied to classify the relationship as trusted. This involves iterating through all possible pairs of individuals, making it conceptually simple but computationally expensive. One key observation here is that trust relationships can be visualized as a graph, where individuals are represented as nodes and trust connections as edges. This insight reveals that solving the problem is equivalent to analyzing the connections in this graph to count trusted relationships. While the brute force method is easy to implement and requires minimal pre-computation, it suffers from a high computational complexity of n squared, which becomes impractical for large datasets, particularly when the number of individuals exceeds 10,000. Given these limitations, we need a more efficient approach to handle larger scales effectively. This leads us to consider an optimized graph-based strategy, which leverages the structural properties of the problem for better performance. Now, let's delve deeper into the graph-based approach. A key improvement here is the use of adjacency lists to represent the graph instead of adjacency matrices. This significantly reduces memory overhead while still allowing us to store and access trust relationships efficiently. Additionally, graph traversal algorithms like breadth-first search, BFS, or depth-first search, DFS, can be employed to explore connections and count trusted relationships. These algorithms are well suited for analyzing graph structures and can efficiently traverse the neighbors of each individual. The trade-offs of this approach are worth noting. On the positive side, it reduces the computational complexity from n squared to n plus m, where n represents the number of individuals and m represents the number of trust connections. This makes the solution far more scalable for larger datasets. However, the implementation complexity increases slightly due to the need to handle edge cases, such as cycles in the graph and disconnected components. Despite these challenges, the graph-based approach is a strong candidate for solving the problem efficiently. Given the alternatives, the graph-based approach emerges as the most practical and efficient strategy. By representing trust relationships as a graph and leveraging adjacency lists, we achieve both memory efficiency and faster traversal of connections. This approach ensures that even as the dataset grows, the solution remains scalable and manageable. The key realization here was that trust relationships naturally map to a graph structure, which allows us to apply well-established graph traversal algorithms to solve the problem. This was a pivotal moment, as it drastically reduced the time complexity and streamlined the implementation effort compared to other methods. The brute force method, in contrast, is computationally prohibitive and would struggle with larger datasets due to its quadratic complexity. Therefore, the graph-based approach strikes an effective balance between efficiency and scalability, making it the ideal choice for this problem. Finally, let's evaluate the trade-offs of the chosen graph-based approach. From an efficiency standpoint, it achieves optimal time complexity, ensuring the solution is fast even for large datasets. Its scalability is another significant advantage, as the linear complexity with respect to the number of nodes and edges allows it to handle problems of various sizes seamlessly. While the implementation is slightly more complex than simpler methods, the performance benefits far outweigh this drawback. Overall, the graph-based approach offers the perfect balance of practicality and performance, making it a robust solution to the problem. By focusing on scalability and leveraging the power of graph traversal algorithms, we ensure that the solution not only meets the problem's requirements but also performs reliably across diverse scenarios. This makes it the most viable and efficient strategy for identifying trusted contacts. To solve the problem of identifying trusted contacts, the first step is to fully understand the problem statement. Here, we are dealing with n individuals, each uniquely labeled from 1 to n. Given a list of trust pairs, where trust I equals A B signifies that person A trusts person B, the goal is to determine which relationships qualify as trusted contacts based on specified conditions. A basic approach to this problem is to evaluate all possible pairs of individuals, which, for n individuals, results in n*(n1 pairs if we exclude self-pairs. This brute force method involves checking each pair to see if the trust conditions are met. Now, let's break the solution into clear, actionable steps. First, we need to parse the input data, which includes the total number of individuals, n, and the trust list, a 2D array where each pair, A, B, indicates that it trusts B. Once the input is prepared, we initialize the necessary data structures. For example, an adjacency matrix or adjacency list is commonly used to represent trust relationships. In an adjacency matrix, if person A trusts person B, we mark it with ADJ, A, B, equals 1. Next, we iterate over all pairs of individuals, I, J, where I is not equal to J, and check if the specific trust conditions are satisfied. For example, if the rule is mutual trust, we verify that both ADJ, I, J, and ADJ, J, I, are set to 1. Pairs that meet the criteria are either recorded or output in the desired format. It's also important to handle edge cases, such as when no trust relationships exist, self-trust entries, or cyclical trust relationships, to ensure the solution is robust. Key insights for this problem include understanding the trade-offs between a brute force approach and optimized solutions. The brute force method evaluates all pairs, resulting in a time complexity of O(n)². Optimized approaches, such as leveraging graph-based techniques, can reduce unnecessary computations and improve efficiency. Viewing trust relationships as a directed graph is particularly useful here. For example, adjacency lists are space-efficient for sparse graphs, while adjacency matrices provide constant-time lookups. Recognizing that this problem can be modeled as a graph problem allows us to apply common graph-related patterns, such as finding cycles, analyzing connected components, or evaluating node properties like in-degree and out-degree. Choosing the right data structure is crucial for implementing the solution efficiently. An adjacency matrix is ideal for dense graphs where most individuals have trust relationships, as it allows constant-time lookups for trust conditions. However, for sparse graphs, where only a few trust relationships exist, adjacency lists are more space-efficient. Another option is using hash maps, which are particularly useful when the individuals are labeled with non-sequential or arbitrary IDs. Each of these structures has its own strengths, and the choice depends on the characteristics of the input data and the specific requirements of the problem. The algorithm's key operations begin with constructing the graph. For each trust pair, A, B, we add an edge from A to B in the chosen adjacency structure. This operation has a time complexity of O(m), where m is the number of trust pairs. Once the graph is built, we can check trust conditions efficiently. For example, to verify mutual trust, we simply check if both A-B and B-A exist in the graph. For one-way trust, we only need to confirm the existence of A-B. The time complexity for these checks depends on the data structure O(1) for an adjacency matrix and O(degree) for an adjacency list. Finally, we handle edge cases, such as excluding self-loops unless explicitly allowed and ensuring no duplicate entries in the result, to ensure the solution is both accurate and complete. The code solves the problem of finding trusted contacts based on trust relationships. First, we initialize an array trust_counts of size n+1 to track the trust score for each person. The value at index I represents the net trust score of the person, positive for being trusted, negative for trusting others. We iterate through the trust pairs. For each pair, A, B, person A trusting B decreases A's trust score and increases B's trust score. This adjustment reflects the trust dynamics accurately. Finally, we iterate through the trust_counts array from index 1 to n, since individuals are labeled from 1 to n. If a person's trust score equals n1, it means they are trusted by everyone except themselves, and thus they qualify as a trusted contact. The result is a list of all individuals who meet this criterion. This solution ensures an efficient traversal of the input data and adheres to the problem requirements. This is the Java implementation of the LeetCode problem, following the same logic as the provided Python solution. The core logic iterates through the trust relationships, updating a trust count array. In Java, we use arrays and ArrayList for the implementation. Key differences include type declarations and the use of Java's enhanced for loop for iterating over the trust array. The result is returned as a list of integers representing the trusted contacts. To solve this problem, we begin by analyzing the first example. Here, we have 3 people, and the trust relationships are given as pairs where the first person in each pair trusts the second. Our goal is to find the person trusted by everyone else. First, we initialize an array called trust_counts with a size of n+1, all set to 0. This array will help us track the net trust score for each person, where a positive value indicates being trusted and a negative value indicates trusting others. Next, we process the trust pairs. For the pair 1, 3, person 1 trusts person 3, so we increment trust_counts 3 by 1 and decrement trust_counts 1 by 1. This gives us an updated array of 0, -1, 0, 1. For the second pair 2, 3, person 2 trusts person 3, so we update the array again, incrementing trust_counts 3 by 1 and decrementing trust_counts 2 by 1. The final trust_counts array after processing all pairs is 0, -1, -1, 2. Now that we've built the trust_counts array, we can determine the trusted person by iterating through the array from index 1 to n. We are looking for a value equal to n1, which in this case is 2, indicating that the person is trusted by everyone else. Checking each index, we find that trust_counts 1 is -1, which means person 1 is not trusted by everyone. Similarly, trust_counts 2 is -1, so person 2 is also not trusted by everyone. However, trust_counts 3 is 2, which matches our condition. This means person 3 is trusted by everyone except themselves, making them the trusted contact. The output for this example is 3. Next, let's examine a scenario where there is no trusted contact. In this second example, we have 3 people again, but the trust pairs are slightly different. For this input, we initialize the trust_counts array as 0, 0, 0, 0. Now we process the trust pairs. Starting with 1, 2, person 1 trusts person 2, so we increment trust_counts 2 by 1 and decrement trust_counts 1 by 1. The updated array becomes 0, -1, 1, 0. Then, 4, 2, 3, person 2 trusts person 3, so we increment trust_counts 3 by 1 and decrement trust_counts 2 by 1. The final array after processing all pairs is 0, -1, 0, 1. Now, to find the trusted contacts, we iterate through the array and check for a value of n1, which is 2 in this case. None of the indices in the array meet this condition. Person 1 has a value of -1, person 2 has 0, and person 3 has 1. None of them are trusted by everyone else. Therefore, the result is an empty list, and the output is. Let's move on to an example where everyone trusts a single person. In this example, we have 4 people, and the trust relationships are such that everyone except one person trusts the same individual. We start by initializing the trust_counts array as 0, 0, 0, 0, 0. Next, we process the trust pairs. For the pair 1, 4, person 1 trusts person 4, so we increment trust_counts 4 by 1 and decrement trust_counts 1 by 1. This updates the array to 0, -1, 0, 0, 1. For the pair 2, 4, person 2 trusts person 4, so we increment trust_counts 4 by 1 and decrement trust_counts 2 by 1. The array now becomes 0, -1, -1, 0, 2. Finally, we process the last pair 3, 4. For the last pair 3, 4, person 3 trusts person 4, so we increment trust_counts 4 by 1 and decrement trust_counts 3 by 1. This gives us the final trust_counts array 0, -1, -1, -1, 3. Now we look for a person with a trust count of n1, which is 3 in this case. Checking the array, we find that trust_counts 4 is 3, meaning person 4 is trusted by everyone else. Therefore, person 4 is the trusted contact. The output for this example is 4. This concludes the solution walkthrough, illustrating how we can efficiently determine the trusted contact using the trust_counts array. To analyze the time complexity of the number trusted contacts function, we break it down into 3 main steps. First, initializing the trust_counts array. This array has n+1 elements, which requires linear time, or O(n), to allocate and initialize. Next, we process the trust list. For every trust pair, A, B, in the list, we adjust the counts for both A and B. Since the list has m pairs and each operation is constant time, this step takes m time. Finally, we loop through the range from 1 to n to identify trusted contacts. This requires n iterations, and each iteration involves a simple comparison and possibly adding an element to a list, both of which are constant time operations. As a result, this step adds another n to our time complexity. When we combine all these steps, the total time complexity of the function becomes n plus n, which simplifies to n plus m. This linear relationship means the function's runtime is directly proportional to the number of people, n, and the number of trust relationships, m. Now, for space complexity, the analysis starts with the trust_counts array. This array is of size n plus 1, so it requires n space. Then, we have the trusted_contacts list, which stores the indices of people who are fully trusted. In the worst case, all n people could be in this list, which also requires n space. Finally, the input trust list is not duplicated in memory, so it does not add to the space complexity. Adding up the space requirements, we get n for the trust_counts array and n for the trusted_contacts list, resulting in a total space complexity of n. Now, let's compare this optimized solution to a brute force approach. The naive method involves iterating over all possible pairs of people, I, j, to check if I trust j, which takes n squared time. Additionally, for each person, another pass through the trust list would be needed to count incoming and outgoing trust relationships, adding m per person. This results in a total time complexity of n squared plus n times m for the brute force approach. In contrast, the optimized solution minimizes the work by using a single pass through the trust list to compute trust scores in m, followed by a single pass through the trust_counts array to identify trusted contacts in n. This reduces the overall time complexity to n plus m, making it significantly more efficient, especially for larger inputs. The time complexity of n plus m remains consistent across best, average, and worst cases because each step of the algorithm processes its inputs exactly once. The performance depends on the values of n and m, but the linear nature of the algorithm ensures predictable efficiency. Mathematically, we can verify this big O calculation. Initializing the trust_counts array involves a single pass over n elements, contributing C1*n to the total time. Processing the trust list requires one pass over m pairs, adding C2*m. Lastly, looping over the n people contributes C3*n. When combined, these steps yield a total time of t equals C1*n plus C2*m plus C3*n, which simplifies to n plus m. For space complexity, the trust_counts array and the trusted_contacts list collectively require at most n memory, confirming that the overall space complexity is also n. One of the most common pitfalls when solving this problem is ignoring edge cases. For example, if the input is empty or contains only one element, many solutions fail to handle these scenarios properly. This is a critical oversight because edge cases often test the boundaries of your implementation. If they're not addressed, it can lead to runtime errors or incorrect results. Another mistake is overlooking time complexity. For instance, using nested loops that have n squared complexity instead of a more efficient approach like n or log n. While this might work for small datasets, it can fail for larger ones due to time constraints. Misunderstanding the problem constraints is another frequent issue. If you assume all inputs are positive when, in reality, negatives or zeros are valid, your solution will be invalid. Finally, hard-coding solutions for specific scenarios is problematic. Your code must be general enough to handle all valid inputs, not just a small subset of test cases. These mistakes can significantly impact both correctness and performance. Another important mistake to avoid is ignoring space complexity. For example, using extra data structures unnecessarily, like storing all elements in a list when only a running total is needed. This can lead to inefficient memory usage or even crashes in environments with limited resources. To excel in interviews, there are several strategies to keep in mind. First, identify patterns in the problem before jumping into coding. Is the problem reducible to a graph traversal, a prefix sum, or a sliding window technique? Recognizing these patterns can guide you toward the right approach. Also, communicate clearly with your interviewer. Break down the problem, explain your thought process, and justify your choices as you go. Start with a brute force solution if you're stuck and then discuss how you might optimize it. Interviewers appreciate a clear progression from a working solution to an efficient one. Always test thoroughly by discussing edge cases and explaining how your solution handles them. Lastly, be prepared to discuss trade-offs, such as balancing time complexity against space usage, to show a deep understanding of the problem. To deepen your understanding, it's helpful to explore related problems. Some examples include LeetCode 217, which focuses on finding duplicates, LeetCode 1 for twosome, LeetCode 49 for group anagrams, and LeetCode 76 for minimum window substring. These problems share underlying concepts and can help you practice transferable techniques. Speaking of techniques, alternative approaches can make your solutions more efficient. Hash maps, for example, are ideal when there's a need for key-value pair relationships or constant time lookups. While they improve time complexity to O(n), they do increase space usage, so that trade-off should be considered. Another effective method is the two-pointers approach, which is particularly useful for problems involving sorted data or comparisons between elements. It reduces the need for nested loops, but it's only applicable in cases where the input structure supports it, such as sorted arrays. These tools can significantly streamline your problem-solving process, provided you apply them in the right contexts. Sorting is another versatile approach to consider. It's especially useful when the problem involves ordering elements, such as finding duplicates or ranges. While sorting adds O and log n time complexity, it can make subsequent operations much simpler. Another powerful technique is divide and conquer. This is well suited for recursive problems or those that can be broken down into smaller subproblems, such as binary search. The main trade-off here is that divide and conquer may require more memory for recursive calls, but it can significantly reduce time complexity. By understanding these trade-offs, you can better decide which approach fits the problem at hand. Each of these methods offers unique advantages, and knowing when and how to apply them can help you craft efficient and elegant solutions to a wide range of problems. Great job! To recap, we discussed problem number 1364, its key challenges, and how to approach it. Remember to think critically about complexity and edge cases when solving similar problems. Thanks for watching, see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!